Welcome to one of the most secretive and crucial production facilities of World War II. This is the Electric Boat Company in Groton, Connecticut, where American ingenuity transforms mountains of raw steel into the deadliest predators beneath the waves. Today, we're taking you inside the complete operation, from the first molten pour to the moment a fully armed submarine disappears into the Atlantic. This is the story of how America built its underwater fleet, one rivet at a time. The process begins hundreds of miles away in the steel mills of Pittsburgh. Massive blast furnaces operate 24 hours a day, converting iron ore, coke, and limestone into the specialized steel alloys required for submarine construction. The Navy demands specific grades, high tensile steel capable of withstanding crushing pressures at depths exceeding 400 feet. Quality control inspectors test every batch, measuring carbon content, tensile strength, and flexibility. Any deviation means rejection. The approved steel is cast into plates ranging from 3/8 of an inch to over 2 inches thick, depending on where they'll be installed on the submarine's hull. These steel plates arrive at the shipyard by rail, stacked on flatbed cars that stretch the length of football fields. Overhead, cranes lift them onto sorting racks, where workers catalog each piece by thickness, grade, and destination. The organization is military precision. Every plate receives a chalk marking indicating which section of which submarine it's destined for. The WWII-class submarine we're building today requires approximately 1,300 tons of steel. That's the weight of 900 automobiles, all shaped into a vessel 312 feet long. In the fabrication shop, the real transformation begins. Workers wearing leather aprons and protective goggles feed steel plates into massive shearing machines. These hydraulic monsters can cut through 2-inch steel like scissors through paper, generating sparks that shower across the concrete floor. The shapes being cut aren't random. Each piece follows blueprints so detailed they fill entire rooms. Naval architects have calculated every curve, every angle, every stress point. The submarine's pressure hull must be perfectly circular in cross-section. Any deviation, even a fraction of an inch, creates weak points where the ocean could crush the hull like an aluminum can. Once cut, the plates move to the rolling mill. This is where flat steel becomes curved. Enormous rollers, some weighing 30 tons, press and bend the steel into the cylindrical sections that will form the submarine's main body. The process requires heat. Workers use oxyacetylene torches to warm specific areas, making the steel more pliable. It's a delicate balance. Too much heat weakens the metal, too little, and it cracks under pressure. Master craftsmen, men who've spent decades learning their trade, guide each plate through the rollers. Their experienced eyes can spot imperfections invisible to inspectors with measuring tools. The curved sections now move to the assembly building, a structure so large it has its own weather system. On cold mornings, clouds form near the ceiling. 7 building ways stretch the length of the facility, each capable of constructing a complete submarine. Our WWII-class boat is taking shape on way number 3. The keel has already been laid, a massive steel spine that runs the entire length of the vessel. Workers are now fitting the curved hull sections onto this foundation. This is where thousands of rivets enter the story. Each submarine requires approximately 200,000 rivets. Teams of riveters work in synchronized pairs. The heater uses a forge to bring rivets to cherry red temperature. He tosses the glowing rivet to the catcher, who uses tongs to grab it midair and insert it into a pre-drilled hole. The bucker-up holds a heavy steel bar against the rivet's head on one side, while the riveter uses a pneumatic hammer to pound the other end flat. The noise is deafening, a constant metallic thunder that echoes through the building. Each rivet must be perfect. A loose rivet means a potential leak, and a leak at 300 feet depth means death for every man aboard. But riveting technology is already becoming obsolete. At the far end of the building, you can see the future. Welders are assembling sections of the next submarine using electric arc welding. This process is faster, stronger, and creates a completely watertight seal. The welder strikes an arc between an electrode and the steel, generating temperatures exceeding 6,000 degrees Fahrenheit. The metal melts and fuses together at the molecular level. It's dangerous work. The ultraviolet light from the arc can blind an unprotected worker in seconds. Everyone wears dark protective helmets and heavy leather clothing. Despite the risks, welding will eventually replace riveting entirely. The submarines being built today represent the transition between two eras of shipbuilding technology. As the pressure hull takes shape, attention turns to the interior structure. A submarine isn't a hollow tube. It's a complex, three-dimensional puzzle where every cubic inch serves multiple purposes. Workers install the frames, heavy circular ribs that reinforce the hull from the inside. These frames are spaced approximately 30 inches apart along the entire length of the submarine. Between the frames, workers fit deck plates, creating the floors where crew members will live and work. The submarine will have 3 decks in most sections, maximizing usable space within the limited diameter. Now comes one of the most critical components, the bulkheads. These are watertight walls that divide the submarine into separate compartments. The WWII class has 8 main compartments, including the forward torpedo room, forward battery compartment, control room, crew quarters, galley, engine rooms, and aft torpedo room. Each bulkhead contains a watertight door, a circular hatch with a wheel mechanism that can be sealed from either side. These doors are lifesavers. If one compartment floods, the crew can seal it off and potentially save the rest of the submarine. Workers test every door mechanism hundreds of times, ensuring smooth operation under any condition. The battery installation happens next, and it's one of the most labor-intensive processes in the entire build. A fleet submarine runs on diesel engines while surfaced, but switches to electric motors when submerged. Those electric motors draw power from massive battery banks. Our submarine requires 252 individual battery cells, each one weighing 1,600 pounds. These aren't ordinary batteries. They're industrial lead-acid cells, similar in principle to a car battery, but vastly larger and more powerful. Workers use overhead cranes to lower them through deck hatches into the forward and aft battery compartments. The batteries sit in specially designed wells below the crew spaces. This location keeps the weight low, improving the submarine's stability. But it also means the crew lives and works directly above tons of sulfuric acid. The ventilation is critical. Batteries generate hydrogen gas during charging, and hydrogen is explosively flammable. While batteries are being installed below, electricians are running cables throughout the submarine. A WWII-class boat contains approximately 50 miles of electrical wiring. Every light, every motor, every instrument, every piece of equipment requires power and control circuits. The main electrical cables are as thick as a man's wrist, capable of carrying hundreds of amperes. Smaller wires branch off like a nervous system, reaching every corner of the vessel. Each connection must be perfect. A short circuit underwater could start a fire, and fire in a sealed submarine is every submariner's nightmare. The electricians follow color-coded blueprints, wrapping each connection with special insulating tape and then securing every cable with metal clips. Nothing can be left loose. When the submarine dives at high speed or surfaces in rough seas, everything inside experiences violent motion. In another section of the submarine, pipe fitters are installing the maze of systems that keep the crew alive. Freshwater systems, saltwater systems, hydraulic systems, compressed air systems, fuel systems, ballast systems. Hundreds of valves, thousands of feet of piping, all precisely fitted and tested. The ballast system is particularly complex. A submarine controls its depth by flooding or blowing tanks with water. Our boat has main ballast tanks built into the spaces between the pressure hull and the outer hull. These tanks can hold over 300 tons of seawater. When the submarine needs to dive, valves open and water floods in, making the vessel heavier than the water it displaces. To surface, high-pressure air blows the water out, making the submarine lighter. Additional trim tanks and negative tanks provide fine depth control. The chief engineer will spend months learning every valve, every pipe, every tank in this system. The diesel engines arrive by truck, massive 16-cylinder Fairbanks, Morse-opposed piston engines. Each engine stands over 10 feet tall and weighs more than 100,000 pounds. These are marvels of engineering, capable of generating 1,600 horsepower, while compact enough to fit through the submarine's hatches. Riggers attach cables to lifting points on each engine and use the building's overhead crane to position them precisely in the engine rooms. 4 engines in total, 2 in each of the 2 engine rooms. Each engine connects to a generator that produces electrical power. When surfaced, the submarine runs on these diesels, which simultaneously propel the vessel and charge the batteries. The engine installation requires microscopic precision. The engine mounts must align perfectly with the propeller shaft bearings, or vibration will tear the submarine apart from the inside. The torpedo rooms are taking shape at both ends of the submarine. The forward torpedo room is the most crowded space on the boat. It contains 6 torpedo tubes, 24 torpedoes in storage racks, and bunks for 18 crew members who sleep among the weapons. Each torpedo tube is a complex mechanism, essentially a giant gun barrel 21 inches in diameter. The tubes must withstand the pressure of firing a 3,000-pound torpedo at depth, and workers install elaborate systems of valves, pistons, and compressed air lines. Firing a torpedo is a carefully choreographed sequence. The outer door, facing the ocean, must remain closed until the last moment. The torpedo is loaded from inside, the inner door is sealed, water floods the tube to equalize pressure. The outer door opens, and compressed air launches the torpedo into the sea. All of this happens in seconds, and every step must work perfectly every time. The conning tower is assembled separately and then lifted by crane onto the main deck. This is the submarine's command center during surface operations and attacks. It's a small, cramped cylinder packed with periscopes, radar equipment, radio gear, and fire control computers. The periscopes are precision optical instruments, each containing dozens of lenses and prisms. They extend from the conning tower down through the control room below, allowing the submarine to see the surface world while remaining submerged. The periscope installation requires extraordinary care. The seals must be absolutely watertight, yet the periscope must rotate smoothly and extend or retract without binding. Now the submarine is nearly complete structurally, but it's still far from finished. The exterior receives attention next. Workers install the outer hull, sometimes called the superstructure. This isn't a pressure-bearing structure. It's a streamlined shell that covers the ballast tanks and creates the submarine's distinctive shape. The outer hull has a deck for surface operations and includes free flooding spaces where water can enter and exit freely. The bridge is built on top of the conning tower, on an open platform where the captain and lookout stand during surface running. It's equipped with wind deflectors, speaking tubes to the conning tower below, and mounts for anti-aircraft guns. The propellers and rudder are installed in the dry dock before launching. The propellers are massive, carefully balanced, 4-bladed screws over 8 feet in diameter. Each blade has a precisely calculated curve that generates maximum thrust with minimum noise. Noise discipline is crucial for submarines. A noisy propeller can be heard for miles underwater. The propellers are mounted on shafts that extend through the after end of the pressure hull. These shaft seals are critical components. They must allow the shaft to rotate at high speed while preventing even a drop of seawater from entering the submarine. The rudder and stern planes mount behind the propellers. These control surfaces allow the submarine to steer and control its angle in the water. Testing begins long before the submarine touches water. Every system undergoes extensive trials. Electricians energize circuits one by one, checking for shorts or faults. Mechanics run the diesel engines, listening for any irregularity in their rhythm. Hydraulic systems are pressurized and inspected for leaks. The critical test is the pressure test. Workers seal every hatch and opening. The submarine is essentially turned into a giant pressure chamber. Compressed air increases the internal pressure to simulate being underwater. Inspectors armed with soap solution walk every inch of the interior and exterior, looking for bubbles that would indicate leaks. Even the tiniest leak must be found and fixed. The ocean is merciless and will exploit any weakness. Launch day arrives months after construction began. The submarine, now painted in dark gray, and designated with its hull number, sits on a massive cradle at the head of the building way. The way slopes toward the Thames River. Wooden blocks have been carefully positioned under the hull. Workers apply thick layers of grease to the sliding surface. Shipyard officials, Navy officers, and invited guests gather for the ceremony. A sponsor, typically a Navy officer's wife, stands on a platform near the bow, holding a champagne bottle wrapped in netting. At the appointed moment, she swings the bottle against the hull. The glass shatters, champagne sprays, and workers simultaneously knock away the restraining triggers. The submarine begins to move, and slowly at first, then accelerating down the greased ways. In less than 30 seconds, over 1,500 tons of steel slide backward into the river with a tremendous splash that sends waves across the water. Tugboats are standing by to secure the newly launched submarine and tow it to the fitting-out pier. The submarine that just hit the water cannot yet dive. It's structurally complete, but far from operationally ready. The fitting-out period will last several more months. This is when the thousands of small details are finished. Workers install all the interior equipment that couldn't be fitted during construction. The galley receives its stoves, ovens, refrigerators, and food storage lockers. The crew quarters get bunks, lockers, and the few personal amenities available on a submarine. The radio room is fitted with transmitters, on receivers, and encoding equipment. The sound room receives its hydrophones and sonar equipment, the submarine's ears that can detect other vessels through the water. The weapon systems require particular attention. The torpedo data computer, a mechanical analog computer weighing over 2 tons, is installed in the conning tower. This device calculates firing solutions, accounting for target speed, target bearing, submarine speed, torpedo speed, and dozens of other variables. It's one of the most sophisticated mechanical computers ever built, with hundreds of gears, shafts, and calculating mechanisms. Fire control technicians spend weeks calibrating and testing it. Below in the forward torpedo room, workers install the torpedo loading equipment, a Davidson chain falls that allow the crew to move 3,000-pound torpedoes around in a space barely large enough to turn around. Each torpedo receives a final inspection. These are Mark 14 steam torpedoes, 20 feet long, carrying 650 pounds of high explosive. They're temperamental weapons, with notorious problems in the early war years, but they're what the submarine will carry into combat. Deck guns are installed and test-fired. The primary deck gun is a 5-inch cannon mounted forward of the conning tower. It's the same gun used on destroyers, capable of firing a 54-pound shell over 10 miles. The submarine also receives 3 20mm anti-aircraft guns and 2 50-caliber machine guns. These weapons are a last resort, but they've saved submarines from air attack more than once. The gun crews practice loading, aiming, and securing the weapons for diving. Everything on a submarine's deck must be secured or removed before diving. A loose item can jam a hatch or create dangerous drag. The crew begins reporting aboard during the final fitting-out phase. A Gatto-class submarine operates with a crew of 6 officers and 54 enlisted men. They're volunteers, everyone. No one is assigned to submarine duty without requesting it. They're also trained specialists. The captain is typically a Naval Academy graduate with years of surface ship experience before submarine school. The executive officer, engineering officer, and diving officer all hold specialized qualifications. The enlisted crew includes electricians, engine mechanics, torpedo men, radio men, sonar men, cooks, and dozens of other ratings. The youngest crew member might be 18. The oldest is probably not yet 40. Submarine duty is a young man's service. The crew begins learning their new boat while it's still pierside. They trace every pipe, every wire, every valve. Each man qualifies on multiple stations. In an emergency, anyone might need to operate any system. The captain conducts damage control drills, deliberately creating simulated casualties to see how the crew responds. Fire in the galley, flooding in the forward torpedo room, jammed dive planes, stuck rudder. The crew must solve each problem quickly and correctly. Lives depend on this training. Sea trials begin with short trips into Long Island Sound. The submarine operates on the surface, testing engines, generators, steering, and radio communications. The crew practices diving and surfacing in shallow, unprotected waters. The diving alarm sounds, a harsh klaxon that can wake the dead. The officer of the deck shouts, "Dive! Dive!" into the intercom. The crew springs into action. Lookouts drop through the conning tower hatch. The bridge is cleared in seconds. Main ballast tank vents open. Air rushes out, water rushes in. The submarine's buoyancy changes from positive to negative. The bow tilts downward. The stern planes are angled to help push the boat under. In less than a minute, the submarine that was cruising on the surface has disappeared beneath the waves. Only the periscope remains visible, a thin pole cutting through the water. The first deep dive is the ultimate test. The submarine proceeds to deep water, off the continental shelf. The captain orders the boat to test depth, 400 feet for a Gatto-class submarine. The crew watches depth gauges intently as the submarine descends. At 200 feet, you can hear the hull talking. Steel plates groan under the pressure. Rivets creak. It's an eerie chorus that never completely goes away at depth. At 300 feet, the pressure is over 130 pounds per square inch, nearly 9 times surface pressure. At 400 feet, it's over 170 pounds per square inch. The crew inspects every inch of the interior. A leak at this depth doesn't drip. It sprays like a cutting torch. Any crack in a weld or failed rivet would show itself immediately. The submarine holds at test depth for hours, proving it can operate safely in the realm where sunlight never reaches. After sea trials come the weapons trials. The submarine proceeds to a designated torpedo testing range. A target vessel, typically an old ship destined for scrapping, is anchored in the range. The submarine approaches submerged, using only periscope observations. The captain orders, "Battle stations torpedo." The fire control party calculates a firing solution. The torpedo data computer whirs and clicks, its mechanical brain processing information. "Solution ready," announces the torpedo data computer operator. "Match bearings and shoot," orders the captain. "Fire 1, replies the torpedo man. A thump reverberates through the submarine as compressed air launches the torpedo. The weapon exits the tube, its motor starts, and it races toward the target at 46 knots. The crew waits. Seconds stretch into forever. Then a distant boom echoes through the water. The sonarman reports loud explosion. Bearing 245. The periscope watch confirms. The target is sinking. The torpedo worked. The submarine is ready for war. Final inspections are conducted by Navy acceptance teams. They examine everything built, installed, tested, and proven over the past year. They review thousands of documents, test reports, inspection records, and trial results. Any discrepancy must be resolved. The Navy is taking possession of a weapon system that costs over $6 million and will carry 60 men into combat. It must be perfect. When the inspection team is satisfied, the commanding officer signs the acceptance documents. The submarine is commissioned into the United States Navy. A commissioning ceremony on the deck makes it official. The American flag is raised. The commission pennant, a long, narrow flag, some is hoisted to the top of the periscope shears. The submarine is now USS Barb, hull number SS-220, a fully operational warship. From raw steel in Pittsburgh to a commissioned warship in Groton, the process has taken approximately 12 months. At the peak of the war, American shipyards were completing a new submarine every 48 hours. The Electric Boat Company alone built 74 fleet submarines during World War II. Portsmouth Naval Shipyard in Maine built 32. Mare Island in California built 17. Manitowoc Shipbuilding in Wisconsin built 28 submarines so far from the ocean that they were launched sideways into a river and then transported through canals and rivers to reach the sea. The submarine pulls away from the pier for the last time, heading not for more tests, but for the Pacific War. I shall stop at Pearl Harbor for final provisions and orders, then disappear into the vast ocean. Her targets are Japanese cargo ships, tankers, and warships. Her weapons are torpedoes, deck guns, and the courage of 60 men sealed inside a steel tube. Some submarines will sink dozens of ships. Some will earn presidential unit citations. Some will never return from patrol, lost to depth charges, mines, or accidents. 188 American fleet submarines were commissioned during World War II. 52 of them, nearly 30%, were lost in action. 3,505 submariners died in those lost boats. But the submarines that survived strangled Japan's maritime economy, sinking over 5 million tons of merchant shipping and over 200 warships, including a battleship and 11 aircraft carriers. The submarine you've watched being built from raw steel to finished warship is more than a machine. She's a testament to American industrial power, to the skill of shipyard workers who built her, and to the courage of the men who took her to war. In 18 months, she'll be patrolling off the coast of Japan. In 5 years, the war will be over, and she'll return home triumphant. But that story begins now, as she slips beneath the waves for the first time with her war ensign flying, heading toward whatever fate awaits her in the deep Pacific. This is how America built its underwater fleet. This is the full operation, from raw steel to the deep sea front line.